Oh. Okay. Hello everyone, welcome back to the afternoon session. We will start with Rucha Kulkarni's talk on half MS for SPLC valuations. She's a postdoc at NUS. Over to you, Rucha.
Thank you, Sanjukta. Hey, good afternoon, everyone. I'll be talking about our recent result, half MMS for SPLC valuations. MMS is maximum share, it's a fairness notion. I'll define what SPLC is and how we get it shortly. This is joint work with Chandra, Pooja, and Ruta while we were all at UIUC. Okay, let's begin. So the key takeaway of this talk is this connection between market equilibria and MMS. Okay, I think that is the one thing that I want to transfer, if nothing else. So we showed this result came out by showing this connection that market equilibrium allocation, if it exists, when it exists, is a fractional 1 MMS allocation. So I'll define what these terms are, but for people who know what these settings are, people have worked on this, while I'm defining for the others, maybe you can try to prove it yourself. The connection comes through Feige defined the APS share. Okay, so market equilibrium, APS is the connection which helps us to show, any price share is the connection which helps us to show that market equilibrium is always 1 MMS. Okay, so let's go ahead. How can we convert this fractional 1 MMS allocation to an integral allocation? Because MMS is a indivisible goods fairness setting notion. We want to combine with, so we want to find a rounding technique that doesn't lose too much. So 1 MMS can be converted into a alpha MMS allocation for some alpha between 0 and 1. Okay, so let's start with reviewing a few of these notions. We have seen them in the previous talks. I'll go over them quickly. So I'll define what the fair division problem is, what the maximum share notion is, what a market equilibrium is before we proceed ahead. So the fair division problem, most of us know the setting. There are a set of n agents. There are a set of m indivisible items. So you cannot cut an item and divide them among multiple agents. There are preferences or valuation functions which associate a real number with every subset of the items. So every agent knows what the real number value is for every subset of the items is. In a lot of settings, most popular fair division work is on additive valuations, where the value of a set of items is just the sum of the values of the items in the set. So it can be, and most of the valuation functions we study, we assume are succinctly represented in some way, okay, either through Oracle access or something else. So given these three things, agents, items, and valuation functions, the objective of the problem is to find an allocation or a partition of all the items among the agents in a manner that is fair. Okay? So that leaves a lot of scope to define what fairness is, exactly what the class of valuation functions is, and a lot of things. So a lot of work is done on this problem. So here we will talk about a particular fairness notion called the maximum share. The value of this share or this notion is defined by the following algorithm. Suppose an agent tries to partition all the goods into n bundles, where n is the number of agents, in a way that maximizes the smallest bundle's value. So we talked about it today morning, that it is an extension of the cut and choose protocol, where suppose an agent were to cut all the objects into n bundles and they were the last one to choose. Then what would be the maximum possible value that the agent could ensure themselves? So for example, suppose you have these values associated with each item, there is one agent, and we want to define the MMS value. And let's assume the valuation function is additive. So the following partition, 3 items in the last bundle and 30, you cannot do better than this in this setting. The worst bundle's value is 30. So MMS is the worst bundle's value. So this agent's maximum share value is 30. So formally, MMS value of an agent is the maximum possible value over all allocations or partitions, minimum valued bundle in that allocation. Okay. And an MMS allocation is an allocation of all the goods among the n agents such that every agent gets a bundle that they value at least equal or more than their MMS value. So note that the MMS value was defined without knowing the independently of the other agents' valuation functions. We just need to know how many agents there exist. And once we pre-compute these MMS values, now we want to solve the fair division problem of partitioning the items among the heterogeneous agents so that every agent is happy MMS wise. So every agent receives a bundle of MMS or more value. So for example, if the agents were all identical, then any allocation that was defining their MMS value, you could give any of these bundles to any of these agents with any permutation, and every bundle has value at least MMS. So this allocation would be an MMS allocation. Okay. In general, when the valuation functions are not identical, it is known that exact MMS allocations do not exist. Okay. There are lower bounds. In fact, for some constant fraction, you cannot guarantee an allocation that gives everyone even a constant fraction of the MMS value for a particular constant. So then we relax our fair division problem, then is the alpha MMS problem. Given the input setting, find an alpha MMS allocation of all the goods among the n agents. Alpha MMS is where every agent receives at least alpha times their MMS value. Okay, great. So now we wanted to study this problem for the beyond additive valuation setting, where the valuation function is more complex, subsumes additive valuations. So it is something more complex than additive valuation setting. So for these for such settings, for such settings, we found this connection of market equilibrium and MMS. So what is the market equilibrium? It is a very natural thing when you think of what a market would be and what would be an equilibrium allocation there. You are a set of agents. Now, in this market equilibrium setting, the goods are assumed to be divisible. You can cut items and distribute them fractionally among the agents. You're given the valuation functions again. The valuation functions are now continuous. They are defined over fractional allocations also. And you are given budgets of the agents. So for this talk, we will assume equal budgets 1 over n, because MMS is defined for equal entitlement. Any price share is defined for unequal. So given this setting where everyone has equal budgets, market equilibrium itself is defined for arbitrary budgets also, but we will not go there for this talk. A market equilibrium output is a tuple of prices for all the goods and an allocation, a fractional allocation that divides all the items, maybe fractionally among all the agents, and satisfies the following properties. So the first property that we want ideally is every agent should buy an optimal bundle subject for that price vector. Okay, so given their budget, the value of agent I for whatever bundle was assigned to them should be the maximum possible valued bundle they can obtain within their budget. So their budget is $1 over $n, and whatever they could buy within $1 over $n, or among all bundles, whatever was the maximum valued bundle they could buy. This property should be satisfied. The optimal bundle property should be satisfied for every agent. Okay. And then you should be able to sell everything, and so all the goods are completely sold and no good is over allocated. Okay, so the allocation is feasible allocation. You're not allocating more than 1 unit of good to anyone. Okay, so market equilibrium is this kind of prices and allocation tuple. So you're able to compute a set of prices and an allocation where together the prices and allocation satisfy these properties. Okay, so now we come to our connection. Okay. I claim that a market equilibrium allocation, if we can compute something like that, is a fractional 1 MMS allocation. Okay. And how I'm going to do that is, I'm going to show first that a market equilibrium value to every agent is an upper bound on the symmetric any price share. The symmetric any price share is the any price share value for equal entitlement, when every agent has 1 over n entitlement. Okay, and that is equal to its dual definition output, and that the dual definition output will be upper bound. I use the dual definition of APS to show that it is an upper bound over 1 MMS. Okay, now the people who already know these terms might immediately be able to see these connections, but let's look at what any price share is and then look at these proofs. So there are two definitions of the any price share value. The pricing definition says that so the motivation was, as we mentioned in the morning, it's from the price and choose protocol. It's adversarially, if somebody else is pricing all the items, then what is the optimal bundle I can choose within this price vector? So that is that min. Yeah, in the APS definition, and the market definition we just now saw does not have the min. So therefore, market is going to be an upper bound. If we could compute the market equilibrium allocation, then the optimal value would be an upper bound over all possible price vectors and then the minimum value among them. Okay? So this is directly shows that market equilibrium value is an upper bound over the symmetric any price share value. Okay, so far so good.
If market switching downwards, asymmetric version also follows.
Yes, so wherever it would exist, I think this upper bound would work for the asymmetric budgets also. Yeah. And now, why is APS at least MMS? I think that was that is much more well known to people who have worked in APS and MMS. So the dual definition of APS is as follows. It is the answer to the following optimization program. It is the maximum value Z obtained as follows. Now you assign weights, non-negative weights to all possible bundles of the items, normalized to sum them all to 1, okay, in the following manner. So you're assigning non-zero weights to all possible bundles of the items. If the value of the bundle is less than Z, then the weight is necessarily 0. And the sum of the weights to all the bundles that contain a particular item, and this is true for every item. So the sum of weights that contain a particular item has to be at most 1 over n. Now for APS, that 1 over n is replaced by whatever the entitlement of the agent is, but we are looking at symmetric APS right now. So this is the dual definition of APS. You want to assign these non-negative weights, and whatever is the smallest bundle's value that you assign the non-zero weight to, that would be your APS value. Okay? So what does this say about MMS? Here is the following feasible solution. You assign weights to bundles using the MMS defining allocation of the agent. Okay, whatever was the partition of the bundles that was defining your MMS value, you assign 1 over n weight to every bundle in the MMS defining allocation and 0 weight to everything else. Okay? So now this is MMS defining allocations are disjoint partitions. Okay, so when you're assigning 1 over n weight, this fourth constraint that every good, the sum of weights of all the bundles containing a particular good, there is exactly one bundle that contains a particular good. So that weight is exactly equal to 1 over n. Okay, and so MMS, so every bundle's value is at least MMS. So Z equals MMS satisfies this feasible solutions value, and we are maximizing over all Z. So APS is at least 1 MMS. Okay, so we had market equilibrium is an upper bound over APS value is an upper bound over MMS. Okay, so now we know that. So how do we get an alpha MMS allocation out of it? Okay, we know we have established that a market equilibrium allocation is the 1 MMS allocation if it exists. Okay, so we wanted to work on the alpha MMS problem for beyond additive valuation settings. So we know that a market equilibrium under very mild conditions exists for this class called the SPLC valuations. Okay, I'll not go into the details of what these conditions are, but it exists. So that means, so right now let us focus only on existence, not worry about computation. But suppose now we know that it exists, how to round it up with a small loss to obtain a alpha MMS allocation. So we show that we can round this market equilibrium allocation with half MMS loss at most for every agent. So you still get half MMS. Okay, so what is this rounding? First, let us define SPLC valuations formally. So these are separable, piecewise, linear, and concave valuations. So most of you have worked on additive valuations by now. This is a generalization of additive. Here you're given copies of items. So you can think of items as types of goods. and then multiple copies of each good are given to you. And the valuation of the next copy over the valuation of n copies of goods is less than n times the value of a single good. So the marginal value of the nth good over n minus 1 copies is going to be smaller than the marginal value of n minus 1, n minus first good over n minus 2 copies. Okay? So the marginal value keeps on decreasing. For example, suppose you have these satellites over here, and you see that the value of just a single copy is 50. The valuation of 2 copies together is 80. So the second satellite adds a marginal value of only 30, whereas the first had a value of 50. So the marginal value keeps on decreasing as you add more and more copies. This is a very natural definition. Most goods, most indivisible goods in the market, most people will have this value that we have decreasing marginal utilities over multiple copies of the same item. And over different good types, the utilities are linear. So whatever are the values over each copies, compute them separately using these decreasing marginal utilities, and then add them up. Okay? So that is separable piecewise linear and concave over each type. Okay? So this is the SPLC valuation setting. And now we want to look at the alpha MMS value, alpha MMS square division problem over SPLC valuations. We already know that market equilibrium exists for the SPLC setting. We want to round it up. Okay. So for rounding it up, a lot of people who have worked on the Nash welfare setting have looked at these rounding techniques. So they may be able to guess what kind of rounding they are going to do. Let's look at that in detail for the others who are not familiar. So we draw something called the allocation graph. Once we come, so we will assume that we have a market equilibrium allocation now, and it is a fractional allocation. So some of the goods are allocated fractionally among the agents. So using this market equilibrium allocation, we draw its allocation graph. So we have the vertices of this graph are all the agents and all the items, and there are edges between items if that item has been assigned to that agent in non-zero fractional amounts. Okay, and whatever items are allocated integrally, we just add them as part of the same vertex as the agent. So we don't have edges between the agent and those items. Okay, so this is the allocation graph. It can be any arbitrary general graph. For SPLC settings, now a very nice observation is that we can always modify this graph such that, and this is the key observation, we can modify this graph so that every agent has at most one copy of that any good that is fractionally allocated. Okay, so a general graph will look like this. So here, for example, the second agent, top right agent, is having 2 copies of the same good allocated fractionally, but we can, and therefore that creates complications because remember in SPLC valuations, the marginal utilities over multiple copies are not linear over each other. So we want to eliminate that possibility, and we can easily modify the graph so that every agent has only at most one copy of every good that is fractionally assigned. So once we do that, now the fractional allocation, now over the fractional allocation, you can see that whatever are the items that are allocated to any single agent, they are all different items, and their value for alpha fraction of particular good plus beta fraction of some other good are just going to be the addition of alpha times that unit goods value plus beta times that unit goods value. And that makes our integral rounding case easier. So once you have this kind of graph, you can make the graph acyclic by something called transferring money spent along any cycles. So suppose there is a cycle in this graph now. So here, for example, there are 2 black edges shared by this agent, and there are these 2 orange edges shared by this bottom right agent, and they are sharing this same 2 copies of goods. So there is a cycle here. We can remove this cycle by considering how much money each agent has spent on each of these edges, and whatever is the smallest amount of money spent, we decrease the money spent on that edge and transfer it on the other edge. So we subtract that money from that edge and add it on the other edge. And we keep doing this cyclic subtraction and addition all over, and we are eliminating one edge along the cycle. And because they are copies of different goods, we can show that the bang per buck, so the value per unit good from each of these edges is the same. So if you're spending equal money, you're taking equal amount of money from here and adding equal amount of money here, the value that you get doesn't change. Okay, so you eliminated cycles, now you have an acyclic graph, and now the rounding is like linear valuation functions. You have an acyclic allocation graph, so it's a forest graph. You root every connected component at some arbitrary agent in the graph, and then give all the children goods to the parent agent successively. That is the entire rounding. So, for example, here you will root it at any arbitrary agent. You look at the tree graph and give every agent whatever the children nodes were. Okay, and that is how you obtain the integral allocation. You rounded up the market equilibrium allocation from the fractional allocation. Okay, so what is the loss we incurred now in this rounding process? In all the previous steps, when we were modifying the graph so that at most one copy was fractionally allocated to every agent of any particular good type, and then the eliminating cycles, there was no loss. Okay, the loss that occurred was only at this last step when we allocated children nodes to every agent. So look at every agent. The number of items lost, the items lost by any agent is just their parent item in this tree. Okay, they got all of their children nodes, they lost one item. So in this kind of rounding, you can find a rounded integral allocation where every agent loses at most one item compared to what they got in the fractional market equilibrium allocation. Okay, so this is what we know so far, and how can we leverage that now? If we can somehow ensure that the largest good has value at most 1 minus alpha MMS, then whatever is lost is at most 1 minus alpha MMS. You started with market equilibrium, which was 1 MMS, so you get alpha MMS value after rounding. Okay, and for MMS, this is a very standard reduction norm, single good reduction, that you can do this pre-processing step for any MMS problem, where if there is a pair of agents and agent and item where the item is of value at least alpha MMS to the agent, then you can greedily allocate that item as a singleton bundle to that agent, eliminate both the pair from and find a reduced instance. And if you can find an alpha MMS allocation in the reduced instance, combined with that singleton allocation, that is an alpha MMS allocation over the original bigger instance also. So you can do these singleton good allocations greedily without loss of generality, without losing anything. So you do that for alpha MMS valued items. Consider alpha MMS valued items. If there are agent item pairs, then allocate singleton goods to any agent who values them to alpha MMS of their value and eliminate that pair. Now do this market equilibrium and rounding process over the reduced instance. So in the reduced instance, there is no pair where an agent values an item to more than half MMS. So every good was at most half MMS value. Okay, so that is the entire algorithm. This is an existential proof. So far, I have not talked about the computability. There is no polynomial time algorithm here because of two reasons. Okay, that should have been. First of all, MMS values are not known and are NP hard to compute, or even for additive valuation settings. And market equilibrium computation for SPLC valuations is a PPAD hard problem. So we cannot hope to actually find the market equilibrium in polynomial time. So how do we get rid of these two problems? We design an upper bound on the MMS value as follows. So you have the following. So what could be in the additive valuation setting, a natural upper bound on MMS values is the average value of all items. Okay? In the SPLC setting, we extend it to whatever its natural extension could be. We take, suppose there are kj copies of a good of type J, then to each agent we allocate kj over n floor of that integral copies, and then 1 over n fraction of whatever is the last copy. So we allocate to every agent kj over n copies, and we look at the value of that allocation, add it over all good types. So every good we allocate kj over n copies. And then we look at the total value of that allocation for the agent. We show that this is an upper bound on the MMS value through something called the concave extension. So this connection we actually showed not just for SPLC, but for submodular valuation functions, which are a superset of SPLC. So concave extension is a particular type of fractional relaxation of valuation functions. I'll not go into the details of what this definition is, but this particular value mu I is at least equal to the concave extension for 1 over where every item is allocated in 1 over n fraction, and that is an upper bound over the APS value. And APS value is an upper bound over the MMS value we know. But this mu I, the important thing is this mu I is polynomial time computation. It's just a formula, you can compute it. So you can use this value to do the singleton good reduction and go to the next step of market equilibrium computation. For market equilibrium computation, now you know that it exists and it gives everyone at least 1 MMS. So because it exists, you can define the following linear program. And you know that the linear program will have a feasible solution where everyone gets at least 1 MMS. Okay. Market equilibrium. So this is a linear function that is kind of capturing SPLC. It is not exactly the definition of SPLC valuation functions. What is the objective is saying that you consider each good and each copy of every good as a separate item, and the value of Vij is the value for agent I of the jth good type and the kth copy of that good. Okay. I should have had a figure there, but for example, if k is the second copy and j is the satellite, then Vij would be value of agent, the marginal value of agent I for the second copy of the satellite good. So the summation ijk is computed. Suppose you were allocating half of the first satellite, half of the second satellite, third of the half of the third satellite, then it would just sum over all the marginal values. And the actual SPLC function does more than that, gives more than that. It will consider, if you are giving 1.5 satellites, it will assume that you get the first copy complete fully and then half of the second copy. So we are actually underestimating by doing this linear extent, by defining this linear value. There is a little technical analysis that I'm hiding, but you can show that this linear program is feasible from the proof of existence of market, because market equilibrium exists, and it gives everyone at least mu I, which is the upper bound we just defined. Okay, so you solve this linear program. It will again be a fractional 1 MMS allocation. Everybody gets 1 MMS, and you can round it in the exact same way as we rounded a market equilibrium allocation. Okay, so we have solved both our difficulties. We defined that upper bound, which is polytime computable, and we do the singleton good reduction using the upper bound on the MMS values. We solve the linear program. The linear program will give every agent mu I value, which is bigger than 1 MMS fractionally. We round the allocation graph by doing all those steps, and the rounding is going to give everyone at least half MMS. Okay, so that is the entire polynomial time algorithm. Okay, so some open questions. One difficult task that we have faced in like just generally solving MMS on beyond additive valuation functions is to find good upper bounds on the MMS value. So even for SPLC, for example, MMS can be as high as value of all the items together. There are examples that we can show. For example, if the second copy has marginal value 0 over itself, and the first copy has MMS value, and there are 2 types of goods and 2 agents. So you have to necessarily give everyone, so the value of all the items together is, the value of all the items together would be 2 MMS in this case. You can define, there is exactly one allocation which gives exact MMS to both. So defining good upper bounds for MMS is a challenging problem. So now the next challenge is market equilibrium doesn't necessarily exist for many beyond additive valuation settings. So to find one MMS fractional allocations which do exist and whose allocation graphs can be made acyclic. So we try to extend this to submodular valuations, but there are a few relaxations of submodular valuations. For example, the standard one is multilinear extensions. We could not prove that the market equilibrium allocation with multilinear extension can be made acyclic. We could prove that multilinear extension can be made acyclic, but the rounding fractional to integral has a further constant factor loss there. The other extension is concave extension. That has no loss when we round from fractional to integral, but we could not show that the market equilibrium graph is can be made acyclic without loss of generality there. So finding fractional allocations which have good MMS guarantees and which can be rounded easily. And then, okay, so in this whole algorithm, the singleton good, if you could eliminate the singleton good reduction, then you could get Pareto optimality also. Okay, because market equilibrium gives a Pareto optimal allocation, and when you're rounding, you're only rounding around the maximum band per buck edges. So you're retaining Pareto optimality. So if you could eliminate the singleton good reduction step somehow, then you could have these PO guarantees also. But of course, that would be fractionally PO, so it would not be as easy because MMS is known to be incompatible with fractional PO. But somehow, to begin trying to solve alpha MMS plus beta PO, can you design an algorithm which gives, let's say, half MMS for additive valuation setting that does not have these pre-computation steps, that does not have the single good reduction step, is another open question. Okay, that's all I had. Thank you.
We have some time for questions.
Okay.
So to reach the approximation ratio of half is this possible for this class of equations?
No, we have proved a counter example that beyond 2/3 MMS doesn't exist.
Better than half this.
At least we could.
Even for submodulars.
So we don't know even half MMS existence for submodular, right?
We don't, but like the
gap is 2/3. Yeah. The counter example is 2/3 even for submodular. Yeah.
Reduction step.
That is for a different problem for alpha MMS plus beta Pareto optimality guarantee. So this whole algorithm, the second step was market equilibrium and rounding the market equilibrium. That whole procedure retains Pareto optimality. Because market equilibrium guarantees PO and rounding is along PO edges. So the rounded allocation is also PO. So if you did not have single good reduction as the pre-computation step, you would have PO here. It is not as direct as that do the same thing and find a market equilibrium procedure which is giving alpha MMS directly. That may not be possible because you know that MMS and because market equilibrium is fractionally PO and it is known that MMS and FPO are incompatible. But yeah, so to begin with, towards answering that question somehow, if you could find just one step process that did not have, I think singleton good reduction is like the obstacle for that. Prop 1 and PO. Okay. Okay. Don't do anything else. Yeah. It's prop up to 1. Yeah, because market equilibrium is prop 1. The rounded market equilibrium is prop 1. That's right.
Is it like you mentioned at the start that the market equilibrium guarantees each agent the APO share? Is it obvious why this can be strengthened to the mu r values you mentioned later?
Yes. So yes, it can be because market equilibrium. The linear program will give the mu r. There is like 2 steps in between, but yeah, it is not that difficult.
We have some time, but if we do not have more questions, maybe we can move on to the next talk.
Thank you.
Thank you, Rucha.
Thank you.
Talking on strategy proof matching of roommates to rooms, and the talk will be by Shivika Narang, who's a postdoc at UNSW. Over to you, Shivika.
Thank you. First of all, thank you for having me here. And thank you all for sticking around post lunch. I know that's not easy. So yeah, I'm Shivika. I will be talking about some joint work with session chair Sanjita and Hadi, who's at Penn State. And this is titled, like she said, Strategy Proof Matching of Roommates to Rooms. And it's a forthcoming AAAI paper. So since Rucha gave me enough time, I am just going to first start with a personal introduction because I realize I've met some of you, but some of you may not know me. Maybe we've not caught up in a while. I spent 7 years at IISc doing PhD and other things. During that time, I visited Hadi at Penn State for a semester, which is where this work started. I visited Rohit last year at IIT Delhi. Since finishing my PhD last year, I have done one semester at SL Math. If you don't know what that is, if you know Simons, it's the math equivalent, also in Berkeley, just on top of the hill, and so it has a better view. But yeah, and right now I'm a postdoc at UNSW. So yeah, in case there was confusion, I work mostly on matching problems. I think one-sided or two-sided preferences as matching problems, whether it's pegging to 1, 1, 1. And for the most part, I look at different combinations of fairness and efficiency in these spaces. This is just some of my work up there. And today's talk is going to actually bring together two things that have sort of been separate, right? So I don't have to tell this audience that matchings are really well studied, whether it's matching agents to other agents, matching agents to houses, items, right? But these are studied separately. Stable matching, stable roommates, kidney exchange, house allocation. In practice, sometimes you have to make joint decisions, right? So maybe you have to assign shared hostel rooms to people, shared offices for people not living in hostels anymore. Maybe you have to pair students for group projects. These settings, what will typically happen is you have preferences about who you're working with, as well as what you will be working on, living, right? So this needs some amount of attention, but like I said, most of the work in this space considers only one dimension of preferences. House allocation assumes whoever is going to live together has decided and they have one joint preference. Stable roommates assumes that wherever you're going to stay is sort of irrelevant. You just care about who you stay with, right? So, like I said, we feel that this needs work. There is a little bit of work. I'm going to call it roommate matching. So very generally, a roommate matching will be you have a bunch of agents who are going to live together in a room. It's going to be two agents to a room. Some people do look at more, right? And as far as we know, 4 papers, these 3, for the most part, are looking at social welfare in roommate matching settings. There's one paper that looks at fairness in the MV3 mess way that some of you might be familiar with, right? One common feature of all 4 of these papers is that they look at additive utilities. So a numerical cardinal value for whom you're going to live with, you have a numerical value for the room, and your ultimate utility is just the sum of those two things. This kind of is more of a substitutionary version of it. It makes sense for some settings, but it need not be true in practice, right? I don't want to live with someone who's going to be a shitty roommate just because I get to live in like this grand palace or something, right? Maybe some people might, I don't. Similarly, like some people will not want to stay with someone just because they get to stay with their best friend. They want to stay really far away from where they're going to work. So you have these type of different preferences, and these preferences are there, even if they're not very descriptive. It might just be 0, 1, like I am new to the college, I don't know who I want to stay with. Maybe I just don't want to stay with someone who wakes up too early, right? I don't want to be woken too early in the day. Maybe I don't want to stay with a smoker. Maybe I don't want to stay very close, very far away from where my classes or my lab will be, right? So you will have some amount of preferences, and you will need both of them to be somewhat acceptable for you to be actually satisfied. And the way we model this is using Leontief utilities. So Leontief just means your ultimate utility will be the minimum of the two things you receive. So if your roommate is worse, it's the value for the roommate. If your room is worse, it's the value for the room. And the overall goal is, under strategy proof mechanisms, we maximize social welfare. We'll talk about social welfare alone a little bit, but mostly that's the goal, right? So let's talk about the model more specifically. You have n agents and n rooms, and your values are given as cardinal valuation functions. So you have Vij is the value of agent I for agent J, and Vi hat, so hat is for the house or the room, for the room, right? And your goal is to make pairs of agents to a room. So each room will be assigned exactly 2 people. Each agent will be assigned 1 other agent and a room. This is not a formal definition of mu, but that's just to give you an intuition. Utilities, like I said, could be additive, but for the most part, we focus on Leontief. And the goal is social welfare. Social welfare, the sum of everyone's utilities over strategy proof mechanisms. Now, unsurprisingly, if you just look at the most general version of the problem, these two goals are sort of incompatible, right? So I'll talk about why exactly, but we use some useful restrictions here. The first one is binary valuations. Now, I know some of us have a tendency to think binary is really restrictive, but binary makes a lot of sense in this setting. Like I said, if you're new to an institute, you're not going to really know, these are my good friends and these are people who are not good to live with. You just have sort of crude 0, 1 preferences about different locations, different sort of things. So binary makes a lot of sense, and it helps us get a really good positive result as well, which is true for Leontief. For symmetric, for additive utilities, we have an additional property that turns out to be useful, which is symmetric valuations. Symmetric just means my value for living with Sanjukta is the same as Sanjukta's value for living with me, for example, right? So now what are our contributions? Firstly, I'm going slow because I have the time, so please feel free to stop me if you have questions, right? So firstly, we introduce Leontief here. We think it's an important concept to be studying here. We also talk about building maximal matchings. Maximal matchings are an important part of matching literature in general, and the few papers that were there already did not really talk about it. So we do talk about it in the paper on different ways to build maximal matchings and what kind of approximation guarantees they give on social welfare. I will not be talking about them today, but the paper is if you're interested, right? The main result is that we show that for binary Leontief utilities, it is possible to maximize welfare and be strategy proof at the same time. This is very surprising, and especially in the context of what I'm going to show you, which is the exact different trade-offs that we see, right? So here I'm for just Leon TF firstly, the problem of maximizing welfare alone is APX hard. Again, I'm not talking about the reduction today. It will be up on the paper. It's similar to a 3DM reduction for those of you who are interested. And in general, if you do not restrict the values, any strategy proof mechanism cannot give you any sort of non-trivial guarantee on social welfare. For binary, like I said, we do show that you have strategy proof mechanisms that can return a maximum welfare. Matching, obviously, this is not going to be strategy proof, it's not going to be polytime. If it were, this would be a different talk, right? The best bound that we have for a polytime mechanism for strategy proofness is 1/3. So the upper bound of 1 is for an exponential time mechanism, 1/3 is for a polytime. For additive, we all general Leon TF. So any values that's non-negative. That's the social welfare, yes. So we get a 1/3. So the numbers here talk about the approximation factor you get on social welfare. For additive, the NP completeness was already known, and you get a matching result that any strategy proof mechanism cannot give you any sort of non-trivial guarantee on social welfare. Turns out with binary also, you cannot do better than 2/3 in a strategy proof mechanism. Whether you take exponential time or super exponential or whatever, it cannot, any strategy proof mechanism cannot give you better than 1/3. 2/3, the best known approximation we have is 1/7. With the addition of symmetric, these things improve to 1/6 and 3/4. So I also want to stress that the APX and NP-complete reductions are for binary and symmetric in Leon TF and additive. So the problems are still NP-hard even for binary. We just see that strategy proofness with Leon TF helps us out a lot. Right? So, okay. So let's first see our impossibility results. Okay. So first we have this very simple example. You have 4 agents and 2 rooms, 2 houses. So an edge between 2 agents or an agent and a room means the value on both sides is 1. Right? So A1's value for A2 is 1, A2's value for A3 and A1 is 1, A2, A3's value for R1 is 1. It's no one. That's life. But yeah, so here you have 2 max welfare matches, either A1, A2 in R1 or A2, A3 in R1. Those are your 2 options, right? And both under the 2 valuations will give you a social welfare of 4. Now, the thing is, if A1 is not matched to A2, they're unhappy. So they can just pretend to have really large value for R1 and R2, so that any guarantee on social welfare that you make, you just inflate the value, you'll end up having to match A1 to A2, right? So for any alpha, they can just scale up the value so high, because your mechanism doesn't know that these values are restricted. There is an incentive for A1 to lie, and similarly, A3 will have an incentive to lie, right? So this is just a very simple example showing when you do not restrict your values, anything like you cannot actually guarantee for strategy proofness and any constant on social welfare. Now, let's look at binary and additive, right? So binary Leon TF, I will soon show you good mechanisms. Binary and additive is also not possible. Very similar example. Now here the thing is slightly different. Only A2 likes R1, no one else cares about any of the rooms. A1 likes A2, so their values, A1's value for A2 is 1, A3's value for A2 is 1. A2 and A4 do not like any of the other agents. right? So now again, you have two max welfare matchings, A1, A2 in R1, A2, A3 in R1. Both of them have a social welfare of 2 because it's binary. Now, A1 and A3 still want to be matched to A2, but they cannot inflate their value for A2. What they return to do is like R1. So if they say, so A2 can say, oh, I actually like R1, so the optimal social welfare would become 3 instead of 2. And so anything that guarantees more than a 2/3 approximation would have to match the person who's lying to A2, right? So this is why anything better than 2/3, however much time this takes, it's a very simple example, so you don't even need a fancy mechanism, cannot be strategy proof. Exact same example, if you make the agent preferences symmetric, gives you the bound for binary and symmetric additive. Okay, now like I said, binary Leon TF is possible. So you have a maximum welfare and strategy proof mechanism for binary Leon TF, can't be polytime. And the way that I'm going to present today is I'm going to show you two mechanisms. First will be a lot more crude, but it gets the job done. And then we build upon that crude mechanism to make a much more refined version, right? So the first one I'm going to call welfare set reduction. This finds all the max welfare matchings first, all of them. So yeah, really has to do a lot of work. Now what I'm going to do, I'm going to construct a series of subsets of this set S0, where S1 will be all the matchings in S0 which maximize agent 1's value. Then S2 is all of the matchings in S1 that maximize agent 2's value, and so on, right? Finally, you end up with S2n, and you just pick arbitrarily from there. So let's go back to our earlier example where we had these two matchings, right? So what is S0 here? It's mu1 and mu2. But so agent 1 has to select from S0. What will agent 1 do? It will just select mu1 because mu2 gives agent 1 value 0, so only mu1 is selected. Agent is happy, gets value 1, so no problems for agent 2. Agent 3 only has mu1 to choose from, right? So the maximum that agent 3 can get is just 0. So again, mu1 is selected, and finally same thing for agent 4, and your result is mu1, right? Simple enough. Now, clearly, this is going to return a matching that is max welfare because it has found all of them. Why is this strategy proof, right? Firstly, if an agent likes the matching return, right? So if they have utility 1, there is no incentive for this agent to win. So why would this be the case? That is Si minus 1 if for agent I. Si minus 1 if it has even one matching that I likes, then Si would have that matching and S2n would be a subset of Si, so you're good. So let's suppose that Si minus 1 actually does not contain any matchings that I likes, right? So all of the matchings in Si minus 1, the utility of I is 0. What has to happen is that I needs to ensure that Si minus 1 has at least one matching that I actually likes, so that it can be selected under the misreported version. So let's see how I can misreport. Now, in a binary Leon TF setting, so the utility agent can get is either 0 or 1, right? It's one if I likes both the roommate as well as the room. Now, for this, what does that mean? If I want to increase the social welfare under this binary Leon TF setting, my original value should have been 0. My original utility in that matching should have been 0. Only then can I pretend that its social welfare has increased. Similarly, to decrease the social welfare from a matching, my original utility should have been 1. Only then can I decrease it. So I cannot increase the perceived social welfare of mu if already likes mu. right? Similarly, you cannot decrease the perceived social welfare for a matching that you don't like. So if S0 does not contain any matching that I likes, I cannot introduce new matchings to S0 that I already likes. Remove any matchings from S0 at all. So in this case, there is no incentive to misreport. If, for example, the only case that is left is that S0 contains at least one matching that I likes, but I minus one does not. So each matching in S0 that I likes would have been eliminated by some prior agent. And this should have been in favor of a matching that some J that comes before I does like, at least one, if not more. So again, to change this set, I actually has no power because it cannot introduce new matchings to J that would be selected. Because if that I actually does like, nor can it remove matchings from SJ that it does not like. So again, there is no incentive to misreport, right? I have not been very formal here, but if you want to go over this argument more in detail, I'm here. But yeah, so this is strategy proof. And like I said, the mechanism is pretty straightforward. You find all max welfare matchings and just reduce from there, right? Now, obviously, this is, like I said, very crude. N factorial, more than that possible matchings that you need to look at. No one has that time, right? What we show now is that you can actually improve it using a three-set packing solver. So how do we do this? I had not intended to go over the details, but I can. So, okay. So the one thing that you have to recognize is that now that each agent has utility at most one, social welfare of a matching can be at most 2n, right? So you can literally iterate over all possible optimal social welfares from 2n to 1 and try and construct matchings that have that social welfare. How do we do that? Now, we pick the highest precedent set of agents not yet tried of size W. So if you start with 2n, the highest precedent set is just all of the agents. And you see, using the three-set packing solver, if there are enough triples that everyone in your set P gets utility 1 and those not in P get utility 0, right? And if there is, you're good. If not, you move on to the next set. If there are no more sets of this size, you move on to the next welfare value, and so on you continue. This, again, sort of constructs a max welfare matching by default. But the main thing is it runs in time C to the n, ignoring lower order terms, for some constant C, right? So, like I said, correctness is straightforward. So strategy proofness, the way we sort of go over it is we show, and this is not that straightforward, and I don't want to get into it right now, is we show that this always returns the same matching as a welfare set reduction mechanism as the one that we just discussed, right? So yeah, so because it always returns the same matching and the older one was strategy proof, so this has to be strategy proof. So that's the main idea. And yeah, if I have really convinced you, the paper is available now. Very recently, it has become available. And like I said, we go over a lot of mechanisms. Maximum matching mechanisms are actually what are giving that end up doing our polytime strategy proof mechanisms as well. So yeah, it's a really fun problem to look at. There's a lot of scope for future work. Like I said, like you can see that there is a big gap in these two values, right? You can try and improve the best known strategy proof mechanism. But yeah, there's also a lot. It's a really interesting model to work on. Modulo the sleepless nights we had on some of this stuff. But yeah, thank you.
Time for questions.
Your
the strategy proof algorithm you had basically involved enumerating all the matchings. My question is, can you compute even one of the max welfare matchings for this problem instance if you didn't care about strategy proofness at all?
APX hard.
Oh, yeah, okay. It's evaluation.
APX hard.
Okay.
Binary and symmetric, it's APX hard.
Thanks.
The reduction is pretty much from, there's this triangle packing problem. You can reduce it from there. You can reduce it from 3DM. Your pick. There's a lot.
It's a stupid question. But can this be similar to if you have more than two roommates? Three roommates plus one?
So there is a few, so out of the 4 papers I flashed earlier, 2 of them actually look at it.
Okay.
The work that they've done, so the fairness paper basically just says NV freeness is NP hard to check for NV freeness in like some law, some like linear number of rooms in the number of agents. Now linear capacities in the number of agents, and they're just 2 rooms. My apologies for the animations. Hey, Bhagwan. But yeah, so this your college dorm and dorm mates thing. This one looks at fairness. Mostly it looks at 2, and then it says that for 3, the fair solution doesn't even exist. The other room allocation with capacity diversity looks at just social welfare and different. So the top 3, the top 2 and the right one also use rents. We're not considering rents in our case, and they focus more on rents and social welfare and prices there. Yes.
So, in the sense that you are fixed ordering and the agents to first get out of it. So, could you
Thank you. That's a great question. We tried to, and those are not strategy proofs. So strategy proofness, this is almost like, if you know serial dictatorship, it's almost like serial dictatorship over max welfare. Serial dictatorship works for strategy proofness really well. If you try to be more fair in terms of max welfare, it's hard. Like, unless if you don't have a specific gen-specific ordering, there are ways to game the system. So we actually in the paper give an example of this.
Okay, thanks. Also, instead of additive, would you better to look at the geometric of the piece so that scaling doesn't
Sure, you can.
manipulations?
We haven't looked at it. It makes sense.
It's the same, right? Leontief and geometric mean it's the same for binary.
For binary, Leontief and geometric is the same.
So,
But for yeah, you can also take logs and add, like he said. I guess it would be more different if you have room capacities and then you're also multiplying across your values for each roommate or something. That might be a little different, but similar. So yeah. You have a question?
Okay, questions?
You could take, yes, like for deterministic, this is the best thing, yeah. We did think about randomized a lot. This is a
Yeah, I think that would be a good extension. We don't know exactly what bounds we'd get if we.
yes, yeah. We don't. So serial dictatorship might go better. Even for serial dictatorship, you do need, like, if you just take arbitrary orders without. We do a serial dictatorship only, honestly, but you have to do some tweaks because arbitrary serial dictatorship can be just 0 approximation. So yeah, I guess random would make sense. Yeah.
Okay, so if there are no more questions, let's thank Shivika and the speakers of the session. We also have an exercise that is a photo session right now at 3:15, so we'll following.
Slowly move away towards, make our way towards.
83, so building 3, you can kind of take a random walk over there and see you there.
Okay, so the photographer is here. So he's the photographer, so everyone is supposed to follow him